All right, welcome back. This will be the second part of your parent functions instructional video. I just wanted to walk through some of the transformations in just a little bit more detail. Now, where I'm pulling this from, if you actually go to your assignment that you will be receiving tomorrow, you can actually find this as well. And then you can follow along right on there. I'll basically do some of your homework here for you. Otherwise, you can just watch and pay attention, and you will see this again tomorrow as well. So looking at this first one for parent functions, we're given the directions of name and sketch the parent function, and then graph the new functions using transformations. Describe the transformations in the order in which they occur, and identify the domain and range. You must have at least 3 accurate points in your graph. So first thing we want to notice about this one is that we are dealing with a cubed root parent function, because we do see a cubed root in it. So our function family name are the cube roots, right? So we're dealing with a cubed root. Okay, now for transformations, so a couple different things. We talked about this in our video a minute ago, but if I have a plus 2 here, remember that means my graph is going to be shifted up 2. The minus 4 there, remember, on the inside is the guy that lies to you. So minus 4 would make you think go to the left, but really we are going to go to the right because he's a liar. The guy on the outside always tells you the truth. So we are also going to go to the right 4 units. Now, once we get there, terrific, but we actually need to graph it. So it does say name and sketch the parent function, which we can do. But at that point, now we really want to actually sit there and get accurate about our graph. So looking at our graph, what we know is this, that our locator point, which for any cubed root always sits right at that center or at the origin, our locator point has now moved up 2 units and to the right 4 units. So our locator point that was sitting right here has now been shifted. It has actually moved up 1, 2, and then to the right 1, 2, 3, 4. So our new locator point is really sitting right there. So that's where we want to put a dot to start our thoughts. Now, finding that locator point is so important because the way you are actually going to graph these is simply by making a table of values. So when I come over here to make my table of values, you can think about this a couple of different ways. So we're going to have X and we're going to have Y. Now, since we already know one of our points, right? We already know our first locator point that happened at 4, 2. So that's actually the one we are going to put right smack dab in the middle of our table. And from there, we are going to work with points that are close to it. So what I mean by that is this. So 4, 2 is our first point. Really, we actually only need 3 points, I think is what they told us. So let's even make our lives a little easier. 4, 2 is one of them. We found that by moving our locator point. And then we're going to just choose points close to it. So the next X value closest to 4 would be 3 and would be 5. And the way we're going to get the Y values is just by plugging them into our function. So if I were to come over to my function and I were to plug a 3 in for X, I would come over here and I would say, okay, 3 take away 4 is a minus 1. And then I'm, of course, looking at the cubed root of a minus 1. The cubed root of a negative 1 is just negative 1, and then negative 1 plus 2 is going to be equal to a positive 1. So when I plugged in a 3, I got a positive 1 out. Now again, you may remember that that is strictly a point. So I get my point 3, 1 that happens right there. From there, we should also plug in 5. So if I go back, I'm just going to erase all my work here, and I'm going to now plug in 5. So plugging in 5, 5 take away 4 is 1. So now I'm looking at the cubed root of 1. The cubed root of 1 is just 1. And 1 plus 2 gives us 3. So again, just evaluating, I get the point 5, 3. Now, this is really where we want to think about what did our parent function look like before. Remember, previously, your parent function for any cubed root function looked something along the lines of this. It was kind of like this S shape. And that's really what our function is still going to be looking like, only it's been moved. So now our graph coming through, here is what our S shape would look like, kind of through the points that we were given there. And that would actually be good enough for the graph of this. Now, by no means am I expecting perfection with this, but you do need to make sure that you accurately have at least 3 points, which we've done because we've graphed boom, boom, and boom. So looking at this, it does ask for our domain. Our domain for this, since it does keep spreading out, will be all real numbers. And our range, it will also be all real numbers. It does keep moving up and down as well. Looking at our next graph here, we are going to have an absolute value, right? So since we see the absolute value here, we can write absolute value. If you want to, you can actually sketch in your parent function as to what that looks like, if that's helpful to you. I can do that right now. I might just do it in kind of a light color so we don't have to erase it necessarily, but our absolute value would look exactly like this. So there's our absolute value. Now, looking at our graph, remember this is where we want to look for any identifiable transformations or movements to our locator point. Our locator point for the absolute value is just that bottom point there. So since I see a -2 here, I know that I'm going to move my graph down 2. And since there's nothing happening inside, it's not going left and right at all. Now, this 2 is in fact happening here, and I'll tell you what the 2 does at the end, but for right now, we're just going to not worry about it. So here's how this is going to work. If my graph is shifted simply down 2, I do know my locator point will move to be right there. Once I know where my locator point is, then I just want to pick x values close to that. So again, I'll make my table. And I only need those 3 values here. So in the middle row is where I'm going to put that locator point. That happened at 0, -2. So what I'm going to do is I'm going to pick the x value before 0, which is -1, and the x value after 0, which is +1. And I'm simply just going to plug those in. If you plug in -1 into this function, the absolute value of a -1 ends up being equal to just +1, right? The absolute value makes a number positive. And that 1 is hooked onto that 2 by multiplication. So 2 times 1 gives us 2. Take away 2 is equal to 0. So that means that when I plugged in a 1, or a -1, I got 0 out. So I will know that I'll have another point right there. If we repeat that process for plugging in a +1, I will have 2 times the absolute value of 1 minus 2. The absolute value of 1 is 1. 1 times 2 is 2. 2 take away 2 is again 0. So I will have a point at 1, 0 as well. Now from there, I can come over here and I can simply graph my line. So graphing my line, or I'm sorry, my absolute value, it's going to look like this. It's still going to look like a V. That green point, our locator point, is still going to be the bottom of it. But what we can see is that our V actually looks a little skinnier. What's really happening here is it's not actually skinnier, it's just taller. If you have somebody that magically gets taller and you stretch them out, they would look skinnier. And the reason that we're seeing that happen here is because of this 2 right here. Now, whenever you have a number out front, what that number is going to do is that number is going to either make your graph taller or it's going to make your graph shorter. So in this situation, since that 2 is there, if that 2 or if that number in front is bigger than 1, it's going to make your graph, well in this case, twice as tall. If that would have been like a 1/3, I would have said 1/3 as tall. right? So it's just really affecting how tall your graph is, and the easiest way to figure out and account for that is still to just make our table. So our domain for this function will be, again, all real numbers, and our range will be from -2 to positive infinity. Let's do one more of these together, and then we're just going to call it for the day. I don't think you're going to have any homework. This really is your homework assignment for tomorrow. So we are just kind of starting it together today. Tomorrow I'll come back and I will work through a few more of these problems just to sit there and help you get more comfortable with this process. So looking at problem number 3, right away we can identify that this is a square root function. Once we know it is a square root function, we want to look for any of those movement pieces to our locator point. So we know it will be down 4. And again, that looks like it should be left 3, so it's really going to be right 3. So down 4. And then we're going to say right. Sorry, I almost tricked myself. 3. So our locator point down 4 and to the right 3 will be located right there. And then this 1/2, we can actually bring that into play right now. We can say half as tall. Right, so up above it was twice as tall, now it's half as tall. So it's going to be a little bit shorter is what that 1/2 is going to do to our graph. Now, since we've located where our locator point is, sitting right there, we can actually make our table quickly. So x and y. And this is where we want to be a little careful. So remember, in our square root function, our locator point is really the tail of that graph. It's that very last point. This is the only one where you don't want that to sit in the middle. So if we come over there, our first point, our locator point, really should be the top one on our table for this. So 3, -4 should be our top value here. And then from there, let's just move 1 to the right of that. So if I move 1 to the right, x would be 4, and then let's just go 1 more to the right, x would be 5. Now, plugging a 4 into this, if I take 4, take away 3, 4 take away 3 is just going to be 1. The square root of 1 is 1. 1 times 1/2, because that has to happen before you subtract 4. This has to be the last thing we do. 1/2 times 1 will be 1/2. Take away 4 will leave us at 1/2 take away 4 would be a -3.5. So -3.5 is what we get for that answer. And that is good enough in terms of finding an actual point for us. Now, after we get done with that one, we're going to go plug in our last one. So now I'm going to take 5 and plug that in. So we're going to probably need our calculator on this one because this is where we're going to run into a little bit of difficulties since we're taking the square root, but we can do it this way. So if I take 5, 5 take away 3 will give us 2. The square root of 2 is going to be an irrational number, so it's going to be ugly to look at. But we can still do it. So second square root 2. So there's our number. And we need to multiply that by 1/2. So we get there, and then if we take away 4 from that, we get to there. -3.29. So if we take that value now, that -3.29, -3.29, we really have our points here. So we have -3, -4, then we have 4, -3.5, and then we have 5, -3.25. And you can start to see that shape kind of show up there that we're used to. That is our square root function. It's just going to be kind of stretched, and the half as tall isn't really helping us out much. Now for our domain will be from 3 to infinity. And then our range will be, since 4 is our lowest y value and we're only going up, -4 to positive infinity as well. So again, ladies and gentlemen, this is just a quick tutorial as to how we start to graph those more accurately using our movement of our locator point. Tomorrow we will go into this in a little bit more depth.